Hey guys, welcome to my second episode of Analytical Mechanics. Well, let's do a quick recap about my last video. Well, in the first video, we talked about some basic concepts in analytical mechanics, such as generalized coordinates, degree of freedom, and one of the most important foundations of analytical mechanics, which is the principle of the least action. And based on that, we derived Lagrange's equation, and it's very, very important because it will be used throughout analytical mechanics, basically. Yeah. And in the last part of the video, we talked about a property of the Lagrange's of Lagrange's function. Is that uh, even if the two different Lagrange function have a difference of this, it's an arbitrary function about generalized coordinates and time, and we take its derivative, despite even if the two different Lagrange function have a difference like this, their equation of motion is the same because the math is here, because this term has no contribution to affect the Lagrange function. It's zero. So in this, that's all about my last video. So in this video, I'm going to talk about some very important conservation laws based on Lagrange's function, which we derived in the last video. Okay, so let's begin. The first concept is energy, and maybe in Newtonian mechanics we have already learned about the conservation of energy. However, how we derive the conservation of energy in analytical mechanics is a totally different approach because I'll explain it. The conservation of energy is based on the homogeneity of time. This term means that with the passage of time, the mechanical state of a closed system remains the same, meaning it's not affected by the passage of time. So we can infer that this term means that the Lagrange's function of the system does not explicitly include time, meaning they will only explicitly include generalized coordinates and generalized velocity. So we can take the derivative of the Lagrange function over time. We will only get these two terms because time will not be explicitly included in Lagrange's function, and we can, after taking the derivative, we can get this, and then we will write it using the Lagrange's function here. We can rewrite the first term into this, and we maintain the second term, and this term we can see that this term is the total derivative of this term. I mean, if we take the total derivative, we can get these two terms. These two terms only take partial derivatives, over here and here. So if so we look at this equation. This term is equal to this, and we can put the summation symbol in here, and so the two derivatives are equal, meaning that its difference, if the derivative of its difference is zero. So if the derivative of this term is equal to zero, it means that this term remains constant, and we call this term energy. Yeah, so this is the first conservation law, the conservation of energy. However, when we use the conservation law of energy, we need to keep in mind that it has a condition. This condition is the conservation law of energy is based on the homogeneity of time, meaning, as I've already explained its meaning. So if the mechanical state of a closed system changes with the passage of time, then the conservation law of energy will not work because it violates its condition. So it can be used. Yeah, and that's basically the first conservation law. So we move on to the second conservation law, that is the conservation of momentum. And it used instead of using homogeneity of time, it used homogeneity of space. Well, this term means that if we move the system parallel, if the system suffer from a parallel displacement, its mechanical state will not change. So it's further condition I will talk about will be talked about later. So next I'm going to introduce a common method, and it's also a very important method that is frequently used in the analytical mechanics. Here, we consider infinite small displacement. That is, actually the location of an object will be RA, vector RA, but now it became vector RA plus epsilon. So this method. Maybe you will not understand it at first. I'm gonna explain it. So, we think of there's a minor, very minor, extremely minor uh, change about the location of the object. However, it will not violate any limitations for the system. So in this condition, we observe the change of the mechanical state of the object, and we will discover something, and that will be very important. So we move on, and we'll see about that. So it's arbitrary, and it's also virtual. It will not move actually. In fact, however, we just imagine there's a difference, and the difference will not violate any limitations for the system. Since it's arbitrary, the change in the Lagrange function will also be zero here. So since only the location of the object changes, we just write this: the partial derivative of Lagrange's function over the vector RA times the difference, that is epsilon, the vector of epsilon, it equals to zero. So since this is infinite small, it's not zero, so this term equals to zero. We substitute this from the result we get from the Lagrange's equation, like this. So, and then we get this. So just by swapping the two symbols, so we get this. So the source of the total derivative of this term to time is equals to zero. So meaning this term is a constant, and we call this term momentum. Well, the condition for the conservation is a little bit different because it uses the homogeneity of space. So it's only conserved on the axis that is not affected by external field. So what did this mean? This means so like if the external field is along the z axis, and then the give me a minute. So the momentum along the z-axis will not conserve, only along x-axis and y-axis. Why is that? Because if the external field is along the axis z, if we move the object along the axis, it will suffer from changes that cannot be neglected. So it will not satisfy the homogeneity of space, meaning the mechanical state of the system will not change if it suffers from a parallel displacement. However, if it moves along the x-axis and y-axis, it will remain the same. So the momentum will only conserve along these two axes. And this is the second conservation law, the conservation of momentum. Now we move on to the third conservation law, the conservation of angular momentum. And it utilized the isotropy of space. By this term, I mean that if the system rotates along the axis and in space, its mechanical state will not change. So it's all about rotation. So then we use the same method. We consider an infinite small rotation of the angle at delta phi, and I try to draw a three-dimensional diagram, and I'm not pretty sure if it looks three-dimensional to you guys. But anyway, so the object moves from point A to point B, and it goes through delta R. Here is an arc, and if we denote this angle as theta and this angle as delta phi, we'll get this. Delta r equals to r sine theta delta phi. So it's just obvious from the diagram, geometry things. And then if we write this in the form of cross product, we get this since it's sine theta. So if we just deduct the direction of for the vectors, we get this. And since the since r is the integral of v, so delta if delta r equals to delta phi cross multiply r the vector r, it's the same for the v, and we keep the angle here the same. And then we study the change in the Lagrange's function. The delta L will be this. There's two changes both for RA and VA here for direction and for location and general location and generalized velocity, just similar to here. So it's almost the same thing, just one additional term. And since the partial derivative of Lagrange's function over RA, the vector RA, it's just what we talked about is its momentum. Is here, and from the Lagrange's equation. So we substitute this term to this, and these two equations into this. Just substitute all these, and we get this. And then we take delta phi out of the bracket to the front, and rewrite all this, but in different orders because we took that out. So we need to consider the directions for the cross product. So it will look like this, and we notice that velocity is the derivative of coordinates, and these two are also taking the derivative. So it's the total derivative time of sigma of the sum of RA is the vector RA times the momentum. So this term is constant, and this is called the angular momentum. There's one more property about the angular momentum is that the value of angular momentum is depends on the choice of the origin. So if we use two different origins and we expect them to be we expect the angular momentum to conserve, it is totally wrong. I'm going to explain here using mathematics. So if we take two different origins, there will be a difference for the location for the vector. Let's assume that the difference of the two different vectors is a, and we put it into the formula for angular momentum, and we will discover that there will be a difference, and it can't be neglected. And this term, it can be neglected. So there's a major difference between these two different angular momentums. So if we want to use the conservation law of angular momentum, we must choose the identical origin for the whole calculation process. And then we're going to talk about the condition for the conservation. It only conserves along the axis about which the external field is symmetrical if there exists an external field, meaning that since it's rotation, so we require that during the process of rotation, the mechanical state of the system should not change. So if the external field is not symmetrical, like let's assume that it's this location just is not symmetrical about this axis. It's just to a straight right. So while we're rotating, the mechanical state of the object will be largely affected by this field. So the angular momentum will not conserve in such conditions. And yeah, that's the three different conservation laws. If you guys have learned about Newtonian mechanics, maybe you will know that in Newtonian mechanics, momentum is written like this. The product of mass and the velocity is vector form, of course. And also, angular momentum is written like this. So maybe you guys will be wondering if these two if the momentum in these two different mechanics will be the same. Well, actually, I'm gonna prove it that it's the same for both mechanics. However, I think the form in analytical mechanics is more of a generalized form. Okay, I'm gonna prove it here. So first, we're gonna work out the Lagrange's function for a single free particle. We consider two different frames. Uh, they have a relative speed of epsilon, and is, of course is infinite small. We start from here, and I guess you guys can understand that there's the fact that the equation for the particles in however in different frames will be the same in terms of form. By this I mean that their the Lagrange function will have such a relationship. I talked about it in the last episode. Although these two Lagrange function have a difference about of this term, these two functions are actually the same because I proved here that this term has no contribution to the Lagrange's equation. It's if we put this into the Lagrange's equation, we'll get zero. So meaning there's no contribution here. So I think the two different Lagrange function in these two different frames will have at most a difference of this. So we substitute for the velocity in the k prime inertial frame here, and we expand it. And here we want to get this term instead of this long expanded form in the bracket. So we use the method called Taylor series. So it's here. The formula is like this. You guys can see it. I think you guys have learned it. I will not mention the proof here. If you guys are interested, you can search it online. Well, we ignore, since epsilon is infinite small, we ignore the things that's above the first order. So the epsilon squared will be neglected. I mean, it's infinite small times infinite small. It's so small that it's so small. So it can, of course, reasonably be neglected. And using the Taylor series, we get this. And since the difference is the total derivative of time about a function about coordinates and time, so these so these two terms will be similar in form. We notice that here, if we take the derivative of q, we get generalized velocity, which is here. So here we can deduct that this term, I wrote it here, this term should be independent of velocity, meaning that if we take the power derivative of Lagrange's function over v squared, it should have absolutely nothing to do with velocity, because if we add more to this, it will not satisfy this condition here. Sorry, this condition here. We take one total derivative of this function, and it should only there's should only be velocity that will appear, and the rest we don't care about the rest. So as I said, uh, this term here, this term should be independent of v, meaning that it should be a thing like constant. So actually analytical mechanics is derived partly from Newtonian mechanics. So in order to make the two fields correspond to each other, we call this term half mass. So this constant is called, because mass always remain unchanged. So we call this constant half of mass, because in Newtonian mechanics, the kinetic energy is equal to this. So in order to correspond with each other, we keep this, yeah, like this. Okay, so maybe you guys will be wondering, why Lagrange's function would have anything to do with the kinetic energy? Well, I'll be explaining that and together with potential energy in my next video. So only for a single particle with no it's not and the single free particle which is not in an external field, its Lagrange's function should be exactly the in the form of the kinetic energy. So now we have already worked out the Lagrange's function for a single free particle. Now we can calculate the three conservation quantities. And first of all, we begin with energy. Well, according to our formula here, we can calculate that the energy for a single free particle would be minus half of m times v squared. Well, energy is actually a scalar. It has nothing to do with direction. So we can here we just ignore this negative here. So its energy is exactly the amount of here. So it's obviously correct in Newtonian mechanics. And then we calculate momentum. Taking the derivative of the Lagrange function over generalized velocity, we get m times v, because we move this times here, and it's just and this we have one. This obviously, if you have learned about calculus, obviously m times a velocity. Yeah, so obviously it corresponds with the momentum in Newtonian mechanics as well. Here, it's all just as a single free particle, so we cannot calculate its angular momentum. But if you guys are interested, you can calculate the Lagrange's function for a closed system with multiple particles, and you guys can calculate one of its angular momentum, and you will find that it will have no conflict with Newtonian mechanics. And yeah, so this. However, analytical mechanics, the approaches in analytical mechanics in my own opinion, is more elegant in Newtonian mechanics, and also it will be more efficient when it comes to more complex problems that we will encounter when we are studying quantum mechanics. Yeah, so I think that's the reason why why analytical mechanics is used more frequently by scientists and physicists. Yeah, so that's all I'm going to talk about today. And in this video, we talked about mainly the three conservation laws, which are energy, momentum, and angular momentum. And when we use that, we need to always keep in mind that it's conditions. You know, here we used different properties, and we need to pay attention to the conditions if we want to use conservation laws. Yeah, and that's all for today. Yeah, thank you guys for watching. See you in my next video. Bye.